Okay, so today we're going to continue our video lesson number 2, which is we are now going to go to our proper lecture about the work and kinetic energy in chapter 6. So let's discuss first the definition of work. Okay, so uh, note that uh, we're particularly interested in the constant force. In this case, okay, this is a special case where you have an object. Okay, so it could be a car, you're pushing it. So you have an object. Okay, so okay, so happen. Okay, so you have an object. So if you have an object, okay, we have here an initial position, and and we have here a final position. So if the object is moving along a straight line, okay, yeah, moving. So first is that moving along a straight line. Okay.
Doing that.
If you
I doing.
working, if you apply a constant force F,
Oh.
so if you're going to apply a constant force F of this object, at and it undergoes a displacement S, okay? So note that the displacement is a straight line displacement and a force is constant, okay? So when a force F acts on a particle that undergoes a straight line displacement, the work, so the definition of work, the work done by the force, okay, the work done by this force, which is F or W on the particle is defined to be the scalar product of F and S. So we know the scalar product is the dot product of the force and the displacement. So the unit of work in SI units is 1 joule or equal to 1 Newton meter. Okay, 1 joule is equal to 1 Newton meter. So you must remember that the work is a scalar quantity. So it can be positive or negative. So depending on the angle between them. Okay. It has no direction in space. Okay. So the work is defined as the scalar product of the constant if the force times the displacement. We know here from our previous lesson in in video number 1 that F dot S is just equal to F as the cosine phi, where if this is the vector F, okay, this is the vector F, and this is the displacement F S, this is the angle between them. So this is just equal to the magnitude of F times the magnitude of S cosine of phi. Phi is the angle between F and S. So that's very simple. Work is defined as the dot product of the displacement, the force, time, and the displacement. So note, in this special case, we are talking about a constant force and a particle which is undergoing a displacement. If the force is not constant, it's no longer the case. Or if the the the, the, the displacement is no longer in a straight line, it's a curve. So there will be a changes to the definition of our work. So this is the simplest definition of our work, where we have constant and straight line space. Okay. So given the definition of a work, okay, we have a example 6.1. So this is a work done by a force. This particular example will teach us how to calculate the work done by a force. Okay, let's read the problem. So you can read with me. So Steve exerts a steady force of 210 Newton. So this is about 471 pounds on a stalled car in figure 6.3. Okay, so since we don't have the figure here, so we have here a car. Okay, so let's just assume this is our figure. Okay, Uh, if he pushes it at a distance of 18 meters, so meaning this car is from this position, okay, moving in a straight line motion. This is the final position. Okay, this is uh apply. There's a force applied, which is we know that the magnitude of this force is equal to 210 Newton. So if you have a car, then you apply a force, it undergoes a displacement, which is the magnitude of 18 meters, straight line displacement. So the question now is that, uh, so the car is also flat. I mean, the car has a flat tire so that it makes the car track straight. So Steve must push it at an, okay. So the car has also a flat tire. So to make the car track straight, so Steve must push it at an angle of 30 degrees. So to make it move in a constant direction or a straight line motion, you need to push it at an angle of 30 degrees. So you need to apply a force so that makes an angle of 30 degrees in the direction of motion. So if this is the direction of motion, so your force must be in this direction, which is uh, this this the displacement. It must have a 30 degrees angle from the direction of motion. So the question now is, how much work does Steve do? Okay, so that's the question for letter A. So if you want to answer letter A, so let's answer first letter A. Okay, so we are given here the definition of work is just equal to F that S, which is equal to the magnitude of F times the magnitude of S cosine the angle between them. Okay, so or we can also rewrite this as just F as cosine of phi. Okay. Okay, now, so we know the magnitude of F, which is 210. We know the magnitude of S, which is 18. So we have here 210 Newton. Okay, we multiplied it by 18 meters. Okay, but however, we don't know the angle. We are given the angle. So this is the case. So this is the force and this is the displacement. Okay, this is an angle between them, which is 30 degrees. Okay, so meaning, so this is the, okay, so meaning, this is actually the work. Okay, so so the work is equal to, okay, so meaning the work done is equal to 200 Newton times 18 meters cosine of 30 degrees. So 210 times 18 cosine of 30 degrees. So we have about 3,273.5 Newton, joules. Okay, so we have 3,273.57.6 Newton meter or joules, Newton meter or joules. So since we have here three significant figures, okay, so let's find firstly chapter 6. So so the answer here is, uh, we have three significant figures. It's about 3.3. Okay. So in the book is 3.3 times 10 to the 3 joules or 33,000 joules. 33,000. 3,000, 3,000. So in the book, the answer is rounded off by 3.3 times 10 to the 3 joules, or this is 3,300 joules. But uh, or But our final answer is the work is equal to 3 to 7 4. So 7 4 joules. So this is the exact answer. Okay, if you do not so the book gives you answer which is very uh, rounded off answer, but in the exam you will show this particular answer. Okay. So, however, if you are since we're dealing in significant figures, so our final answer is three significant figures, and we have here the two significant figures. So our final answer must be in two significant figures. That's the rule of multiplication. So uh, our book, our final answer here is 3.3. So two significant figures times 10 to the 3 joules. So if your instructor gives you instructions to follow the significant figures, you can give this answer, or you can, if not, you can give this answer. Okay. So now we are going to answer number 5. Okay, let's answer number 5 and letter B. So in the helpful mode, Steve pushes a second stalled car. So Steve is very helpful. He pushes a second stalled car in a steady force given by the force which is in unit vector form. So we have the x component and a y component. So then the displacement of the car. So after he applied a force, steady force, constant force, it undergoes a displacement in vector form also. How much work does Steve do? Okay, in unit vector form. So by our first video, so we showed that the the formula for the dot product. Okay, so this is the work. The other one is Fs cosine of phi, and the other one is the work F dot S is just equal to so if you recall, if A dot B is equal to AX BX plus AY BY plus AZ BC. So in this particular case, we have Fx. So because our uh, vector has Fx I hat plus Fyj hat, and our this vector here S is equal to Xi hat plus Yj hat. So meaning we have Fx times X plus Fy, okay, times Y. So because our AX is Fx, our BX is X, our AY is Fy, our BY is Y, and we have no Z component. Okay, so this means that we have 160 Newton. Okay, this is our Fx times 14 meters. Okay, plus a negative 40 Newton. Okay, times 11 meters. Okay, so here we have the so our answer must be in two significant figures. Okay, so if we are going to use our calculator for this particular problem, so we have 160 times 14 plus negative 40 times 11. So we have 1,000. So our answer is 1,800 Newton meter or joules. Since our answer must be, or if your instructor asks you to follow the rules of significant figures, so your work must be in two significant figures is 1.8 times 10 to the 3 joules. So that is our answer for our letter B. So work done by a constant force. How about if you are given a problem where there are several forces acting on the uh, object? Okay, we just like this example, we have a sled where there are several forces acting on it. So in our chapter 5, we already discussed that about the forces such as the normal forces, the tension force, the kinds of forces, the friction force, and the weight force. Okay, we know that in this sled there are forces acting on it. Okay, let's read the problem first and apply the concept work. Okay, so the work done by several forces, example 6.2. So a farmer hitches her tractor to a sled loaded with firewood and pulls it at a distance of 20 meters along a level ground. So this is the sled loaded with firewood, okay? And the farmer hitches her tractor, so it is connected to a tractor and pulls it at a distance of 20 meters. So meaning there is a displacement which is equal to uh, uh, 20 meters. Sorry for that. Which is equal to 20 meters along a level ground. Okay. So the total weight of the sled and the load is 14,700 Newton. So the tractor exerts a constant force at an angle of 36.9 above the horizontal. Okay. So a 3,500 Newton friction force opposes the led's motion. So the question now is find the work done by each force acting on the sled and the total work done by all the forces. Okay. So for to have give you an idea how many forces acting on the sled, okay, because find the work done by each of the force the sled, okay, it is better to use use the free body diagram. Okay. Let's draw the free body diagram of the sled. Okay. Or for the sled. Okay. So meaning, so we're gonna create a free body diagram. This is our x, this is our y. So we know that there is a normal force acting on the sled along that direction. We have the normal force. So we also know that there is a weight force. Okay, the weight force, and we also know that there is a friction force F, and a tension force. So we have a friction force and a tension force, which is 30 degrees. Okay, that's the tension force. So we have here the tension force, which is around 36.9. Okay, 36.9 degrees. So those are the forces acting on the sled. Okay. So in the problem, so it undergoes the magnitude of a vector. So it undergoes in the x direction, which is 20 meters. Okay, 20 meters. So in this direction, okay, in the positive x direction. Okay. So the question now is find the work done by each of the force acting on the sled and the total work done by all the forces. How do we do this? Uh how do we answer this one? Okay. So first, let's go to definition of work. So the work again is just equal to the force times the displacement. Okay. So the first thing since we know that there is a normal force, the weight force, the tension force, and the friction force, since we know that, uh, we can now find the work done by each of these forces. So the first one is the work done by the normal force. So by definition, we have the normal force times the displacement. Okay. So we have the N as cosine of phi. Okay. So before we answer this, let's sketch the direction. Okay. So if this is our normal force along the y direction, okay, and our displacement force, okay, this displacement vector is along the x-axis, okay, this is along the y-axis. So meaning the angle between them is 90 degrees, okay, and so meaning this is the n as cosine of 90 degrees, okay. So we know that the cosine of 90 is just equal to 0. Cosine of 90 degrees is just equal to 0. So meaning the work done by the normal force is equal to 0. Okay. So so it means that whenever a force is perpendicular to the displacement, so the work done by that force is 0. Okay, you need to remember that. So it depends on the angle. It could also be negative, positive, depending on the angle between the forces. How about the letter? So the work done by the weight force. Okay, the work done by the weight force. Okay. So we have the weight force times the displacement. Okay. Or the weight times S cosine of. Okay. So before what we know what is the angle. Okay. Okay, what is the angle between them? Let's draw a sketch first. Okay, sketch. Okay. So this is the direction of the weight force. Okay, along the uh, negative y. Okay, and this is the direction of the displacement along the positive x. Okay, so there are plenty of so we also know that this is also perpendicular. The angle between them is 90 degrees. Okay, so meaning this is also 90 degrees, or it could be negative. So if you read this one clockwise, it could be negative 90 degrees or 270 degrees, but it's the same, 0. Okay. So even you put this one as 270 degrees, okay, cosine 270 degrees, it will give you 0. As long as it's perpendicular, okay, cosine negative 90, 0, okay, cosine 270 is 0. So as long as it's perpendicular, so yeah, you could also write this on as cosine of 270 degrees, or weight times the displacement cosine of negative 90 degrees. So depending on where did you read the angle. So if you read this one clockwise, or you read the counterclockwise, or just the just determine what is the angle between them. It's 90 degrees. So and the same, both are eh, each of them is 0. Okay, as long as the force is perpendicular. How about letter C? The work done by this friction force. Okay, the work done by this friction force, which is the friction force that the displacement is equal to the F times S cosine. So let's determine the angle with the sketch this one. So in this case, this is the displacement along the S. However, the friction force is in the opposite direction, along the negative x direction. Okay. So if this is the case, the angle between them is 180 degrees. Phi, 180 degrees. Okay. So we have 180 degrees, which we know that cosine of 180 degrees is just negative 1. Okay, so we have the the what we call this one. The magnitude of the friction force is 3,500 Newton. And for our displacement is 20 meters times -1. Okay. 3,500 times 20 is 70. Okay. 70,000. So which is 70,000 joules. Or, so in two significant figures, 7.0 times 10 to the 3 uh, times 10 to the 4, 1, 2, times 10 to the 4. Okay. Times 10 to the 4, okay, joules. Or mga 70,000 joules. Okay. However, this is negative because we have -1, so this is negative 70,000 joules. However, for the letter D, the work done by the tension force, okay, we have the tension force, which is at an angle 36.9. So, tension force is the tension that does this one. Okay, okay. So the tension force, okay, let's determine the tension force. If you sketch the tension force, so this is our tension force T, and this is our displacement. So this is our y, this is our x, and this is our displacement. And the angle between them is 36.9. So very simple. The magnitude T, the magnitude of the displacement, cosine 36.9. So we have the tension force is given, which is 5,000. Okay, 5,000 Newton. We multiply this one by the 20 meters. Okay, cosine of 36.9, which is 5,000 times 20 times cosine 36.9. So this is our answer will be 79968.5 joules. Or in two significant figures, so we have uh, so this is around 8.0 or 8.0 times 10 to the 4 joules. 8.0, or this is 80 kilojoules. Okay. So now if you want to find the work total, okay, if you wish to find the work total, okay, see the work total. So let's have another color. Okay, the work total. The work total is just equal to the work done by the normal force plus the work done by the weight force plus the work done by the friction force plus the work done by the tension force. So here we have 0 plus 0 plus -7.0 times 10 to the 4 joules plus 8.0 times 10 to the 4 joules. So we have positive 1.0 times 10 to the 4 joules, or around 10,000 joules. Okay, so that's the final answer. So the work total is 10,000 joules. Okay, so here in our particular problem, the total work done is 10,000 joules. And each of the work done by each of the forces is 0 for the normal force, 0 for the weight force, negative 70,000 joules for the friction force, and 80,000 joules for the tension force. So overall, the total work total is equal to, or the total work is equal to 10,000 joules.
coming, Daddy.
Thank you for watching. If you enjoyed this video and you want to see more physics tutorials like this, don't forget to hit the subscribe button and turn on the notification bell so that you never miss an update. Your support means a lot to us and help us create more content like this. Also, feel free to comment below with any topics you'd like us to cover in future videos. See you next time.